All right, let's jump right into one of the most bizarre, most profound, and honestly most important ideas in all of physics. This is a puzzle that totally stumped even Albert Einstein, a genuine mystery that cuts to the very heart of what reality even is.
And get this is what he called it: spooky action at a distance. With those three words, Einstein basically called out what he thought was a huge problem with quantum mechanics, something so weird it just had to be breaking the fundamental rules of the universe. The question is, was he right? Was it a flaw, or was it a clue to something much, much deeper?
So here's our game plan. We're going to unpack Einstein's original puzzle, and then we'll get into the huge debate that came next. We'll see how one brilliant physicist turned this whole thing into a real experiment, and then find out how this spooky stuff was actually proven to be real. We'll also bust the #1 myth about entanglement, and then we'll look at how this spooky idea is kicking off a whole new technological revolution.
So just to be clear, Einstein was okay with most of quantum mechanics, but he had this one massive problem with a specific prediction it made. It seemed to violate a sacred, common-sense rule of the universe called locality. You know, the simple idea that if you poke something here, it can't instantly affect something way over there on the other side of the galaxy.
And this kicked off a massive debate, really a story of two completely different versions of the universe. On one side, you had Einstein, arguing that there must be some hidden rules we just can't see yet. And on the other, you had Niels Bohr and the quantum team, who argued for a universe connected by these strange instantaneous links.
And at the center of it all is this thing called quantum entanglement. The key idea here is that these two particles basically behave like a single object. Imagine they're created together, then they fly apart, maybe to opposite ends of the universe. Well, according to quantum mechanics, they stay perfectly connected, their fates forever linked as one system. And that leads to two wildly different views of reality. So on the left, you've got Einstein's view, which we call local realism. He thought particles have definite properties from the get-go. We just don't know what they are. It's like having two sealed envelopes. One says yes, one says no. The answer is already inside. You just have to open it to find out. But on the right, you have the quantum view. It says the properties are totally fuzzy, they don't even exist until you look. And the moment you measure one particle, its partner, no matter how far away, instantly snaps into a corresponding state.
Einstein's idea feels way more intuitive, and this light bulb analogy shows why. Imagine you have two boxes. You know, one has a red bulb and one has a blue one. You ship one box to the far side of the galaxy. When you open your box and see a red light bulb, you know right then and there that the other one has to be blue. There's no spooky communication happening. The information was already there from the start. Makes sense, right? Seems pretty logical.
So for decades, this was just a debate. You know, Einstein says this, Bohr says that. Who's right? There was absolutely no way to know. It was just philosophy. Until a physicist named John Stuart Bell came along and basically changed the game forever.
Bell's incredible insight was realizing that these two versions of reality weren't just philosophical. They actually made different predictions about the world. You could test them. He came up with a mathematical proof, an actual test that could ask nature itself. Okay, which one is it? How do you really work?
And here's the absolute heart of it. Bell's theorem predicted that if you measured these entangled particles in a very specific way, the statistics would give you the answer. In Einstein's local universe, the results could only match up about 67% of the time, at most. But in the spooky quantum universe, the results would be much more strongly connected, matching up 75% of the time. You see that? There's a clear, measurable difference. The challenge was laid down. It was time for an experiment.
So, with Bell's test in hand, a whole new generation of physicists got to work. They were going to build an experiment to, well, force the universe to show its cards once and for all.
This journey took decades. Back in 1972, John Clauser was the first to pull it off. And his results? They sided with quantum mechanics, not Einstein. Then, in the 80s, a land aspect came along and did an even better, more loophole-free version. And finally, in 2022, Clauser, Aspect, and a third pioneer, Anton Zeilinger, were awarded the Nobel Prize. I mean, that's the ultimate stamp of approval for changing how we see the universe.
But what I love about this is the human side of the story. John Clauser, the guy who did that first big experiment, later admitted he was actually betting on Einstein. He thought that quantum predictions were just too crazy to be true. He fully expected his own experiment to fail, to prove Einstein was right all along. But instead, it proved the spooky stuff was real. Okay, so this whole instantaneous connection thing naturally leads to a huge question, a really big misconception. If measuring a particle here instantly affects one across the galaxy, does that mean we've found a way to send messages faster than light?
It's the first thing everyone thinks of, right? If you can flip a switch here and instantly change something light years away, that sounds exactly like a faster-than-light communicator.
Well, the answer, believe it or not, is a hard no. It's impossible. And the reason comes down to this one really important distinction. Correlation is not the same thing as communication. Let me break it down. When you measure your particle, the result you get is completely and utterly random. It might be spin up, it might be spin down, but you have zero control over which one it'll be. So you can't force your particle to be up to send a 1 or down to send a 0. The only way you even know the spooky correlation is there is if you get on the phone with your friend on the other side of the galaxy and compare your list of random results with their list. And that phone call? Well, that's limited by the good old speed of light. So, if it's not a faster-than-light telephone, why should we care? What's the big deal? Well, the big deal is that learning how to control this spooky connection is paving the way for a complete technological revolution.
And I'm not exaggerating. This isn't just some weird thing physicists talk about anymore. We're talking about massive investments, billions of dollars. Governments and corporations are betting that entanglement is going to be as crucial to our future as the silicon chip was to the last century.
And what kind of technology are we talking about? We're talking quantum computers that can solve problems that would take today's best supercomputers billions of years. We're talking about ultra-secure quantum networks where any attempt to listen in would instantly break the entanglement and get you caught. And yes, even a form of quantum teleportation, where you can transfer the exact quantum state of a particle from one place to another. All of this is being built on the foundation of Einstein's spooky action.
So, there you have it. We started with a philosophical puzzle that bothered Einstein, it turned into a Nobel Prize-winning experiment, and now it's sparking a revolution in technology. It just goes to show you that our everyday common sense is sometimes just wrong. That reality is so much weirder and so much more interconnected than we ever thought possible. And that leaves you with one final question to chew on. What else are we getting completely wrong?